Okay, so good morning. So I thought then I'm going to actually help the in context as the solutions we provide. The stories were based on our own customers with strong location. Generically, so introduce ourselves. So we are in Hangzhou, China, and from the picture, his city, it's also where the Alibaba headquarters is based. So our founding members are most have been contributing to the internal Google Cluster Management System and the open source Kubernetes projects. Also, as a proud member of CNCF, we are also promoting meetup, training sessions, certification, as publishing articles or even books. So if any of you, whoever wants to speak at one of our events, so do contact us. So it's very welcome. Also, as a company, providing service products to help transform their IT infrastructure. So the stories and the morals were expected from our own customers from a wide array, from the e-commerce, finance, carrier, in the traditional industry, stateful app and legacy. So yeah, just a first quick check. So not know Kubernetes. Kubernetes has become a kind of a common sense, right? So in KubeCon or in the US. So the question is, how is, okay, so is that, need to speak too loud? All right. So you may wonder how Kubernetes is doing in China. And these photos were taken from our meetup events. So they can pretty much give the answer. We have held about 2 meetups every quarter in China, and there are hundreds of attendees in each of these events. And we have got about 3,000 followers on our Kubernetes study group. So that is the status of the Kubernetes in China. So basically, there is the thriving community with growing user base and engaged partners. So before I dive into the details, I wanted to give a quick summary of what we found upfront from our case studies. So first, the positives. We found one of the biggest reasons that people buy into Kubernetes in China is due to the strong community and the big brand names behind it. And also, people loved its native service-oriented design and elegant API and architecture. Especially, it is very extensive. And also, it provides rich functionality compared to Swarm or Mesos. So it goes really beyond just scheduling and resource management. It also provides a lot of configuration management, network policy, secrets, etc. So they're not just about resource management or scheduling. But in reality, so we also found there are some factors that affected Kubernetes user experience. So from the list, you can see some of them are due to the different environments between the US and the Chinese enterprises, the different cloud providers, and also people's operational habits. Because in China, so most of the operators are more familiar with user interface, right? So they're not so much a big fan of command lines. When people do get Kubernetes up and running, So there are also some pitfalls we found that need to also be addressed in order to run Kubernetes continuously and successfully in production systems. So this one is a short list. For example, for the first one, so even though we know Kubernetes has the notion of resource quota and the limits, but in practice, how to set the exact values for them represent a big challenge. Because if we set the quota too low, then applications may crash because they usually require a higher CPU spikes when they start up. But if we set the quota too high, that may result in a very low utilization, right? So these are the challenges we have to resolve. And again, so these are the common challenges we've seen in our own customers, but they could be seen in other places as well. All right, so in the second half of the talk, I'll gloss over some of these challenges and present our solutions. And the good news is, so some of the solutions are open sourced, so contributions are welcome. So the first thing we have to do is to get Kubernetes deployed, even without internet inaccessibility, right? So when looking at the title, people may think of, okay, so this is probably due to like the firewalls, right? But in fact, surprisingly, it's a quite frequent requirement in some traditional industries or some like state-owned companies, like in energy or in banking or finance, where all the communications have to happen within their own private corporate network. So to complement the upstream deployment instructions, we devised a Ansible-based deployment mechanism. So the gist is basically to pre-download Kubernetes packages, Python packages, and a bunch of YAML sources files. And we also need to localize our Docker registry by populating it with a bunch of pre-saved Docker images. So speaking of deployment, from our own experience, deploying Kubernetes in our or in on-premise or bare metal environments accounts for about 70% of all the cases. And the other 30% of customers deploy Kubernetes on public cloud. But in China, pretty much all the 30% is Alibaba Cloud, right? So in fact, Alibaba Cloud is already among the top 3 largest cloud providers or the public clouds in the world. And also it has the fastest growth rate. So which means we have to integrate Kubernetes with a bunch of like components like the computing service, the load balancer, and also the object storage service, right? And we also put together a pull request with our work in the PR linked here. So once we have a running Kubernetes, the next thing we have to do is to migrate existing applications into the new platform. And one of the things that developers actually are concerned about is how to do logging, right? So if we recall, this is the standard way of doing logging. So where we recommend applications to write their logs onto standard out or standard error, right? Instead of writing to file. And then Docker or some other container runtime will like intercept the messages and write that into a local JSON file under a Docker directory. And now Kubelet will come into play and set up a soft link to map that file into a directory that FluentD can recognize, right? And FluentD will now script the files, attach some additional metadata, and send the file into the Elasticsearch store that comes with Kubernetes, right? So this is the standard model, and it should work in most cases. But however, we found there are some limitations where this model doesn't work as well as expected. So the first thing is, in some traditional industries, people or legacy applications still write to files, right? So if we wanted to require to use that model, it means people have to change their code or applications in order to use Kubernetes. That may become a big hurdle to some enterprises. And also surprisingly, so that's not the only reason. So sometimes people have a kind of legit scenario where they wanted to use different files to actually segregate logs, even from the same application, right? So if we are using the standard out approach, so basically all the messages from the same application writes to the same JSON file, right, generated by Docker. And also, we found some enterprises already have an existing ELK or storage platform for the logs. So they wanted to reuse their existing platforms instead of using the ELK stack built into Kubernetes. So here's our enhancement. So now, in order to allow people to still write files for the logs, so we first set up an empty directory or the empty dir storage option for Kubernetes and mount that into the application pod. So from now on, the application will write logs into that empty directory. And so the next step is to modify kubelet to still set up a soft link. But this time, it's not mapping from the Docker's JSON file, but it is mapping from the empty directory generated by Kubernetes. And again, map that into the directory that FluentD recognizes, right? And now, so FluentD can do a similar thing, but it'll also attach a metadata about the file name from which the logs are collected. And finally, when sending the logs, we also tweak FluentD so that we can point FluentD to send the logs to anywhere beyond just the built-in Elasticsearch platform. So this is our enhancement. So another possible option would be to use the sidecar pattern, where we have a sidecar container for each application pod. And that sidecar will collect the logs and pipe that logs to any existing like a logging platform. But after experiments, we found that approach actually requires more resource because you have to deploy a sidecar for each of the application container in your system. So after logging, like kind of a twin problem is monitoring, right? So again, let's first review the current standard approach for monitoring in Kubernetes. So essentially, we're running a CAdvisor agent on each node or each machine. And on top of them, there's a centralized heapster that collects and aggregates all the metrics from CAdvisor, persists those data in InfluxDB, and finally, Grafana will visualize and present all those metrics in very nice format. So again, so this works pretty well in most cases, but in a large-scale production environment, so it represents, it incurs some challenges. For example, the heapster or the InfluxDB themselves are single points of failure, which also incur scaling issues. And also, if people are familiar with the internal cluster management in Google, which we call Borg, so there is also a Borgmon, a system that monitors the Borg system itself. So if we look at Kubernetes, even though this architecture monitors the applications running on top of Kubernetes, but nothing monitors Kubernetes itself, right? So because Kubernetes itself is also a complex software system with like kubedns, kubelet, and all the networking setups. So there is no such kubemon to monitor the system components. And finally, there is no alerting. So operators, in our case, have complained about, so they said, we cannot stare at our like Grafana dashboard 24/7 in order to detect any anomaly, right? So we need to have a automatic and intelligent alerting module to send any like alerting emails or short messages. So this is our enhancement. And this is the overall picture. So you can immediately notice we have replaced two components. So the first one is for the storage, we used OpenTSDB instead of InfluxDB. And also we used Prometheus instead of Heapster for scraping the metrics. And these are the rationales why we made the change. Oh, and also I forgot to mention, so there is also a alert manager that aggregates the metrics and also performs like alerting based on the user's rules. So now these are the rationales of why we did these two replacements. So the first one, the reason we're using Prometheus is because it supports really powerful querying language. So it's very nice. You can very easily craft your own query to see how the system is behaving. And also, we are using OpenTSDB because it is based on HBase, so it has much better scalability in nature, and it can be horizontally scaled. But also, there are like challenges coming along if you want to use these two approaches. For example, to use OpenTSDB, so you have to deal with how to run it on top of Kubernetes. And also, you have to deal with some very devil details like solving the reverse IP lookup problem. All right. So after logging and monitoring, so what is the next tricky business? So to us, it is achieving external load balancer, right? So recall that in our cases, about 70% of all the deployments happen on-premise or on bare metal. So how, in these cases, how can you expose external services without a cloud provider, right? So if you're using like AWS or GCP or Azure, so you can use their like public load balancers to balance traffic from the outside into your internal services, right? But it's a luxury for on-premise or bare metal deployments. So let's see what are the options currently in the upstream. So the first one, and probably the easiest one, is to use a node port, right? So just a quick recap. So essentially, if you want to expose a service to the external world, so you can use a node port, which opens a high port on every machine, right? So in this case, it's 31.080, right? So it's open on every machine in the cluster. And under the hood, so essentially, Kubernetes will set up a bunch of IP table rules to actually redirect the traffics. So if any traffic comes to that port, so these rules will come into play and randomly redirect the traffics to the multiple backend instances behind that service. So this is the node port approach. So we can think about, so what are like the limitations for this approach, right? So any guesses? So the first one is all the outbound traffic or the external traffic has to target at a single machine. And the destination address is like IP colon port, right? So it still represents a single point of failure and also incurs scaling issues. And also because the load balancing is done via IP tables, so it only supports level 4 load balancing. So you cannot do like session affinity or like a load balancing based on like client regions, etc. Right. So just a quick summary. In upstream, so currently we can do external load balancers through like cloud load balancer providers, node port, or Ingress. So Ingress is a new concept, right? So in Kubernetes 1.4. But again, they all have some limitations. Like I already mentioned, so public cloud providers are not always available. Node port is kind of hacky and not highly scalable. And Ingress, so which is a new cool concept, is nice, but its current implementation in the upstream only supports using GCP to perform the load balancers, right? So what if we wanted to do a on-premise or a bare metal deployment? So here is our solution, right? So we call it HiAvailable Ingress. So in order to gather, so let's first see how the default Ingress works. So essentially, if you want to use a Ingress, so it'll deploy an Ingress pod in one of the machines in your cluster. And this Ingress pod will do basically two things. So the first one is to set up a cloud load balancer, which could be on GCP. And also, it'll automatically generate forwarding rules based on the user's preference. And after that, so all the incoming traffic will hit the GCP load balancer first, and then according to the rules, it'll be redirected to any backend instance. So this is how the upstream ingress works. But we can see, so one of the other limitations for that is there is only one ingress pod running in the system, right? So again, not highly available, not really scaling. So that's why we need to have a highly available ingress. So from this example picture, we can see that. So first, we can deploy more than one ingress pod in multiple machines, right? So probably the font is too small, so it's not really readable. But we can just imagine. So this one is the ingress controller, right? So we have two of them, all right? So now it has a new problem. So now we have two ingress controllers. Before, for all the incoming traffic, it can just directly hit into the only one ingress controller. But now we have two of them. So how can we do the load balancing for the ingress controllers themselves? So our approach is to basically use keep alive D, so that keep alive D will maintain a stable virtual IP. And this virtual IP will be assigned on multiple machines which run the ingress controller. For all the incoming traffic, so keep alive D will guarantee that there is only one active instance, one active ingress controller at any time. And all the incoming traffic will be routed to that active ingress controller. And within this ingress pod, so there is also a HA proxy or Nginx running in it, so that we can configure level 7 forwarding rules to support like session affinity and more complicated load balancing rules, right? And this HA proxy or Nginx will be in charge of further directing the traffic to a backend pod for that service. So this is a basic model for the high available ingress, right? So yeah, things are looking better than the single ingress controller case. But there are like still remaining problem with this approach. So if you want to make a guess, so we can see that. All right, so before I get to that, so let's first see how this high available approach will handle failures. So again, back to the picture where we have two ingress controllers or two ingress pods running on the two machines on the right side. So assuming now like the ingress controller on the rightmost failed, and then so migration will happen. So first, the application containers running on the failure machine will be migrated to a healthy machine on the leftmost side. And also, the ingress controller pod will also be migrated, as the arrow denotes, to the healthy machine on the leftmost side. All right. So now, keep alive D will come into play and correctly also maintain the mapping from the stable virtual IP to the new machine, so that all the further traffic will come into the new healthy machine instead of the failed machine. Right? So this is how the high availability helps in this case. All right. So now let's think about the problems with this approach. So the first one is we may encounter what we call a reload storm, because remember all the forwarding rules are now being taken care of by the HA proxy or the Nginx. So if any of the pods with the behind the service failed and there is a migration, so we have to update. So by we, I mean the ingress controller pod. So it's automatic, so it's better than manual. But we still have to update like the config files for Nginx or HA proxy, right? So this is for one service. But imagine if we have like hundreds or thousands of services and each with like tens of pods. So the probability for this update is very high. And we have to reload the configs for the HA proxy or Nginx pretty often, right? So this is what we call the reload storm. And also there is the scaling issue as well, because even though we have multiple instances of the ingress pods, but they still have to take care of the forwarding and the load balancing for all the hundreds or thousands of services, right? So it can still represent a scaling issue. And to solve this problem, we actually introduce the scheduling, like the scheduling of jobs, that concept into here. All right, so here is the gist. So we essentially performed a sharding. So suppose we have multiple ingress controllers. instead of letting all of them to handle all the services, we perform a sharding so that some of the ingress controllers are only taking care of a subset of the services. And they will only perform load balancing as well as like forwarding for those subset of services, right? So it basically resembles a scheduling scenario where we have like a bunch of services and we have another bunch of ingress controllers. So we have to assign which ingress controllers take care of which subset of services, right? So it's a scheduling problem. So to solve that problem, we introduce a new concept called the ingress claim, right? So an ingress claim, if you recall the PVC, the persistent volume claim, is pretty similar. So you define a class of forwarding like service upfront. So again, so the font is too small to read. So, but basically, these two black boxes define two ingress claims. So each with different like performance guarantees, like what is a delay, what is a timeout, and what is like the bandwidth for this ingress claim. And now let's see how things work. So first, we add a new controller into the master component, and we call it the ingress claim controller. So what it does is whenever there is a request for a new service to be exposed externally, so it submits a request to the master saying that, hey, I want it to be exposed externally, so please assign me a ingress controller to take care of my all my forwarding and load balancing. And also it requests a certain ingress claim class saying that I want it to have a very low like latency to do my load balancing. And this ingress claim controller will look at, are there any suitable ingress controllers already in the system? And if not, so it'll create the certain number of ingress controllers for that service, right? So in this example, there are 2 instances, and the number 2 actually comes from the ingress claim. So it's also a property for the ingress claim class, right? Because that means how reliable you want it, you want your like load balancer to be. All right. So that's pretty much about our high available ingress mechanism. And the last tricky business I wanted to mention is how to achieve high availability masters. So you may already noticed it's kind of like an option already in the upstream. But the problem again is the upstream solution requires to use like GCP or AWS load balancers in order to achieve this high availability, right? So, but in bare metal or in on-premise cases, we basically have to devise our own mechanism to achieve this. So the reason is, intuitively, if we want to have high availability master, we have to deploy multiple instances, right? So as depicted here, so we have multiple master instances running in here. But again, the problem is now when traffic comes, so to which of these master instances should we redirect the traffic? Again, so we need a load balancer. So it's similar story. So we use a keep live D and a HA proxy in front of all these master instances to achieve the high available load balancers themselves. All right. All right, so in the remainder of the talk, so hopefully I'll talk about like something more interesting. So for the previous like the issues we mentioned, so they are kind of the enhancements to the core Kubernetes like components. But in order to run Kubernetes smoothly in a production system, so Kubernetes alone is not enough, right? So we have to have a way to do like continuous like integration and a deployment, and we also need to have like a registry, a Docker registry or like an image registry to securely store the images. So now let's see how we solve those problems with some open source efforts. So the first one I wanted to introduce is a system called Cyclone. So this is our open sourced CICD system, and it's more Kubernetes native. So people today may have been using like Jenkins with like either like plugins or some custom scripts in order to like integrate Jenkins into a container platform. But Cyclone is Kubernetes native, so it is more lightweight and it is much faster. So it basically ships your code directly from your source repository to any Kubernetes cluster that you specified. It also has some very nice properties that Jenkins or some other CI/CD tools do not have. For example, so we know the modern world is all with microservices, right? But another challenge with microservices is now it has too many components. So when you're doing a push or you're doing a release, so there are like multiple components that you may have to update at the same time, and they may have like interdependencies, right? So if you change the API of a backend, you probably want to update that first and then update your front end. So in order to better support that, so Cyclone is dependency aware. So it supports an API and in the near future a UI that lets the user to use a drag and drop approach to first set up a dependency graph like shown here in the picture. And so then when you are doing a release, so it'll follow the dependency order and it will start from the root. So that is dependency awareness. And also, we know that about 60% of the Docker images have some like suspicious portion in them. So security for the Docker images is also very important. So we integrate in Cyclone with Claire to basically scan each layer of the Docker images against a database of known like vulnerability signatures in order to detect any like suspicious code in the base image or in any layer of the image. So this is like a sample output from Cyclone. All right. So this one is how it is designed, but I'm not going into the details. So you can visit our like GitHub page for more details. So I also mentioned we also need to have a private registry to store the Docker images. And the options out there are probably like either Docker Hub or like the standard Docker registry distribution project, right? So those are open source as well. But we are using an open source project called Harbor. So Harbor was initiated by VMware, and we are one of the official partners on that project. So this link here is our fork, but from there you can look at the upstream, the VMware version. So the reason we're using like a fork here is because so in our version, so we have a more concise user experience or UI. So where on a single page you can see various image details about like different images, like where are they deployed, when are they like updated, and who did which updates, etc. And also another novel feature we introduced here is labeling. So if we think of the canonical Docker image URL, so it's basically just 3 layers, right? So you have the registry location / the project name or the namespace, right? / basically the repo name. Of course, there is the label in the end. But so in our cases, so for some of the large enterprise users, they wanted to have a more flexible like labeling mechanism to really enable them to classify and manage images more flexibly. For example, they want to classify images per their customer, so they may in a like ISV industry, right? Or they may store and classify images by types or by regions, right? So if you think of just the canonical the image names, so how can you express this information? So of course you can put everything into the tag, right, in the very end, or put that into the image names, but these are like hacky. So we basically borrow the concept of Kubernetes, right? So if you think of how Kubernetes manage its resources, so it is using like labels, right? So we're doing the same thing. So you can tag any Docker image with any number of labels, and then you can use the APIs to query those labels in order to perform like management and classification. Right, and besides these features, of course, it is highly available, compared to the like the Docker distribution or the Docker registry. And also it has a nice feature of automatically syncing images between multiple instances of this Harbor registry. And what is even better is we also enabled a one-click deployment of Harbor on Kubernetes so that we can make Harbor even more highly available. So this is an example like user interface for Harbor. All right, so the last point I wanted to mention, although I'm running out of time, is big data support. Because it's a pretty often requirement to run some big data applications on Kubernetes as well, although it is not very well officially supported in the upstream, right? So people maybe are still running more like stateless applications on Kubernetes, but we wanted to do big data. So besides like Hadoop and Spark, so here with maybe 1 or 2 minutes, I wanted to highlight our work for running TensorFlow on Kubernetes. So for those of you who are not familiar with TensorFlow, so it's a deep learning tool, also open sourced by Google, which uses neural networks to perform some more efficient learning on non-structured data, right? Like pictures or like audio files or et cetera, right? So essentially, the architecture for TensorFlow is the server and worker model. So where the server essentially stores all the parameters for the training model, and the worker is the one that really performs the prediction and the classification and the actual job. So in order to run TensorFlow on Kubernetes, the gist is to use the job concept in Kubernetes so that you first start the TensorFlow server, and whenever it needs to start a worker, so it basically creates a Kubernetes job to do that. And also to achieve more reliable effect, so we can set restart on failure policy for that job to finish. So to summarize, so our takeaway for how to increase the Kubernetes user base in China or maybe in a global scale is basically threefold. So the first one is easier deployment. It's not only about having like a one-click deployment solution, but it's also more about being able to deploy Kubernetes in a more like diverse environments, either with or without internet access, either with or without AWS or OpenStack. So this is number one. So number two is in order to use Kubernetes in a large, especially production systems, we have to do more like performance tuning and optimizations. And finally, as the case for any active projects, so we always require like better documentation and training as well. So and probably for like non-English speaking countries, so any internationalization is also preferred. So that's pretty much conclude my talk. And finally, I also wanted to thank two of our team members who are also Kubernetes contributors. They're also here, like Deyuan and Ming Qiang. So they're also helping a lot with all this work and preparing the slides. All right, so it seems we only have 1 minute to go. So I would like to take any questions. Yeah.
You talked about using TensorFlow for the big data. Are your customers, you mentioned Hadoop and Spark, are they also doing Hadoop and Spark work?
Yes, they do. Because like historically, like Hadoop and Spark, these are more like mature and more like well-understood tools to the customers. Yes, so they're using Hadoop and Spark actually more frequently than TensorFlow.
But inside the Kubernetes?
Yeah, inside Kubernetes customers, clusters, yeah.
What do they use for data storage?
So data storage, so these are different options. So 30% of the customers who are using like Alibaba Cloud, so they basically use like the object storage service, it's a public cloud. But for our like on-premise storage, we basically use Ceph in order to do that. Yeah. All right, so if you have further questions, so I'll be around to chat. Thank you very much.